distance. Okay, continue. Okay, so good morning, early in the morning, and depending on the place of the world you're living now. In my place, Canary Islands, is very, very early in the morning. Also in Austria, I think so. And for most of the presenters we have today. So this is an exciting session. Congratulations for all these papers we're going to present. So yeah, we just know we have 20 minutes for. I am professor of economics in University of La Laguna. So you have each speaker have 20 minutes of presentation, and after that we have more or less 10 minutes of discussion and question. So we have this first paper that by Lukas Kranzl and many other authors. Okay, there are 7 authors, so I'm not going to read all of them. The title of the paper is Potential of Efficient Heating and Cooling in the Light of Decarbonization Targets in the case of Austria. So it is your turn, Lukas.
Yeah, thanks, Gustavo, for this introduction, and good morning, everybody, or at least for those who where it is morning. Yes, so the title of my presentation is Potential of Efficient Heating and Cooling in the Light of Decarbonization Targets, the case of Austria. The background and motivation of this work is the European Energy Efficiency Directive, which in Article 14 asks member states to carry out a so-called comprehensive assessment of the potential for an efficient heating and cooling supply every 5 years, starting with 2015. And we did this work for the Austrian government already in 2015, and now again with the end of 2020. So, and from this work that we did for the Austrian government and the Federal Ministry of Climate Action, I took out for this presentation as a main research question, what are economic potentials of efficient district heating supply in Austria by 2030 and 2050? And connected to this question, which type of areas can and should be supplied by district heating? What is an economically viable district heating supply mix in different types of district heating systems and in Austria in general? And connected to this question is also the question of what is the role of the carbon price, which I will also discuss a little bit. And yeah, what are drivers for the uptake of future district heating potentials? Just to clarify a few points regarding scope and system boundaries, the focus is on space heating and hot water preparation. So industrial process heating was considered for industrial waste heat supply, but not for the rest of the study. When I say efficient district heating, I refer to the definition according to the Energy Efficiency Directive, and I'm aware that this is currently under revision, but still I refer to this existing definition. And a third point, and I think that's quite relevant to understand the outcomes and also some underlying assumptions. The study assumes full climate neutrality of the Austrian energy system until 2040. Because this is what is set in the current governmental program and on the Austrian level, and also with the European Green Deal on the European level, more or less. What we did were these 6 steps. So we started with the survey of the status quo of heat demand and distribution, existing supply infrastructure, and so on. Then in the second step, we analyzed the potential of industrial waste heat as a potential to be fed into the district heating networks. Step 3 is the identification of regions that could potentially be suitable for district heating based on heat distribution costs. These regions that we identify were then clustered into regions with similar characteristics regarding size, resource availability, and existing infrastructure. Fifth step is the calculation of the costs for the heat supply, both for district heating supply and the individual decentral object related supply. And finally, we identify the economic potential for efficient heat supply, and in particular, the economic potential of district heating by comparing costs for district heating and district decentral supply in each of these clustered areas. Or actually in each of the identified potential district heating regions. In my presentation, I will focus on steps 3, 4, 5, and 6. So I will not go into detail regarding the survey of the status quo and the analysis of potential of industrial waste heat, because that's quite another task and challenge. So to describe the methodology in a little bit more detail, so we started with step 1. Calculating the costs of heat distribution on a hectare level for the territory of Austria, and identified those areas where these costs of heat distribution are sufficiently low to allow for district heating. Then we clustered these region types in step 2. And calculated in step 3 the cost of heat generation, both for district heating and for decentral heat supply. And by comparing this district heating supply and the decentral supply, we come up with the district heating potential. So step 1, identification of regions that could potentially be suitable for district heating. And I already said this is based on heat distribution costs. And what we need in the first place is the expected or possible development of useful energy demand for space heating and hot water in Austria. And here we took scenarios that have been developed for the Austrian government 3 or 4 years ago. Consisting of a so-called VEM with existing measures scenario, achieving energy reduction due to retrofitting and efficient new building construction of about 1/3 up to 2050, and the so-called transition scenario achieving about half of energy savings due to more ambitious, more effective building renovation strategies. And these heat demand scenarios are converted into heat demand maps on an hectare level. This is shown for the exemplary case of the baseline or base year in 2017, and this has been done as well for 2030 and 2050, and for the cases of the with existing measures scenario and the transition scenario. And now, taking these heat density maps, these future existing and future heat density maps, we can identify for these different cases feasible, or for the different scenarios, economically feasible distribution district heating areas just from the distribution costs point of view. And so we need to set first which scenario do we mean. Do we consider the with existing measure or transition scenario? Do we consider year 2030 or 2050? And then we also need another assumption which I didn't mention up to now, the so-called what we call connection rate. So this is the share of buildings, the share of energy demand, heat demand within a certain district heating supply region connected to the district heating grid. And we know that in some areas this is around 40%, 50%, but of course it's more effective to connect a higher share of buildings in order to make use of this infrastructure more effectively and reduce also heat losses. So we also know that there are district heating grids with connection rates up to 90, 100%. So we distinguish these two cases of 45% and 90%, and we can say, okay, what are the acceptable the heat distribution costs, 30, 40, 50 euro per megawatt hour. And for each of these cases, we can then draw this map of potential district heating scenarios and district heating areas. So now we have identified these potential district heating areas. We need to cluster them. We need to cluster regions with similar characteristics. Why? I will explain this later. Because we want to identify efficient district heating supply mix for each of these regions, and doing it for all these a few hundred potential regions would be too much effort. And so what we did, we said, okay, there are 4 larger cities representing 4 major district heating regions, Vienna, Graz, Linz, Salzburg, which we considered as separate regions. And then we clustered the remaining about 600 regions into 6 remaining district heating region types, depending on gas availability, geothermal potential, waste heat potential, river size, and the question whether there is already an existing heat network available. And we did this by a so-called, this clustering approach that we did can be visualized in this dendrogram, where we see that we selected 6 clusters according to the distance of each of these clusters in terms of the dimensions I mentioned before: gas availability, district heating, grid surface water, geothermal, waste heat on different temperature levels. And now in the third step, we calculated the costs for heat supply for each of these representative cluster. This was done by a standard dispatch optimization model developed in the Horizon 2020 project Hot Maps. This standard dispatch model has as an objection function to minimize the total costs minus the revenues, in particular revenues from electricity sales in case of CHP plants. Main inputs are the heat demand of the potential grid. So we take our heat density map a starting point and assume a certain connection rate and get the heat demand of the grid. Then we assume a certain mix of installed capacities of heat generators, and we have identified for each of the clusters 3 portfolios to be tested. I will come back to that later. We need, of course, energy prices, load profiles, radiation profiles, temperature profiles, electricity price profiles, hourly profiles, and receive as main outputs the heat generation costs, investment, operation, fuel costs, heat generation mix, CO2 emissions, full load hours. So what did we do with this model? We have these 10 region types that I explained before. And then we calculated 2 years, 2030 and 2050, in 2 different assessment methods, which are actually given. Also, the terminologies are given by the Energy Efficiency Directive. We calculated a so-called financial assessment from the let's say macroeconomic point of view. What is the profitability, the economic viability from the investor's point of view, and the overall let's say societal economic point of view. Then we distinguish the different heat demand scenarios, different energy carrier and CO2 prices, and technology portfolios, where the first one is predominantly gas. The second one is the gas with a higher share of renewables and excess heat, and the third one is predominantly renewables and excess heat and very little gas remaining. So to be a little bit more precise here, you can see that the use of local resources increase from portfolio to portfolio 1 to portfolio 3. Biomass has been put moderate in all the 3 portfolios because there is already a quite significant share of biomass in the Austrian district heating grid available. And the main difference was actually that we decreased gradually gas and increased not only local resources but also air source heat pumps. Because even with low COP in winter time. This is more or less available in all areas. A few words on the energy carrier prices and CO2 prices. So we, in the economic scenario or assessment method, we had different CO2 prices. In the economic scenario, we assumed external costs of CO2 emissions of 300 euro per tons, whereas in the financial assessment method, we assumed for 2030 CO2 price of 81 and about 180 euro per ton in 2050. The interest rate is different for the two assessment methods, and also the inclusion of taxes. And an important assumption, and that's why I also want to share it here, is the costs or price for green gas. We, due to our assumption of full decarbonization from 2040 on, it is clear that in 2050 fossil gas has no place anymore in the heat supply. So we need to replace all the gas which would remain by green gas. And so we needed some assumptions on the share of power to gas, hydrogen, and biomethane, and also the related costs which we took from literature, and end up with a green gas costs in 2030 between 68 and 93 euro per megawatt hour, in 2050 about 88 to 128 euro per megawatt hour. And in 2030, the blending of green gas to the total gas grid is only about 6 to 7%, but in 2050 it's 100%. So, and how do the results look like? I picked one exemplary result of this cluster 7. This is a cluster with where we grouped regions with already existing district heating grids, a gas infrastructure, and high potential for river water source heat pump. And what you can see here is always these three portfolios under the two economic assessment methods, the so-called financial and the so-called economic assessment method, under high prices and low prices, and under different energy demand scenarios, and under for the 2 years, 2030 and 2050. And you see the optimal use of the resources for each of the portfolios, and also the resulting levelized cost of heat supply on the right-hand axis, in the form of these red triangles. And what we can see here is that, in particular, under for 2050, portfolio 3 tends to be the cheapest one, although there are also some scenarios where portfolio 2, with still a little bit lower share of air source heat pumps, can also be interesting. Because, and why is that? Because there is this potential of river source heat pump, which here depicted in brown, which reduces the required amount of gas, depicted here in blue. But all the scenarios where we need higher amount of gas turn out to become less cost effective. Of course, due to the need to replace fossil gas by green gas, which is expected to be not so cheap. So this is the way how we present the scenarios for each portfolio, and then we can now compare the costs of the supply from district heating with the decentral supply costs, and doing that for each of the identified potential district heating areas. We see that in each of these areas is depicted here by a dot, and the red lines represent the average levelized costs of the average cost of levelized cost of individual heating. And we see that in 2030 there are still a number of areas which where the district heating is not sufficient, not economic, so where the individual system would be more cost competitive, but in 2050, under the assumptions that we took here, individual costs of the level of cost of individual heating turn out to be higher than the optimized district heating system for more or less all the or a very high share of the scenarios. So when we sum up all the results on the Austrian scale, we see that, and we can depict the total useful energy demand as the red dots, and the blue ones are the useful energy demand for the district heating potential. We see that district heating can cover between 10 and up to 50% of the useful energy demand, depending mainly on the connection rate, and that's the main message. We can also show this picture for the energy carrier mix, where we see that biomass holds still a significant share, but heat pumps in particular increase their share both in decentral supply but also in district heating. Due to time reasons, I will come to the conclusions now, which are: assuming full decarbonization of the heat sector, gas turns out not to be a cost-effective option in the space heating sector, neither for district heating nor decentral. Based on our assumptions, gas-fired power plants will only have limited full load hours by 2050. Thus, the role of CHPs for district heating supply will decrease. Thermal storage systems are becoming increasingly important. We see this in particular in the more advanced portfolios, although they also see a high uncertainty regarding the cost of thermal storage systems. So this is a crucial point, I guess, for the future. One of the key messages is achievable connection rates have a major impact on the economic potential of district heating. So that is also where policy and spatial energy policies are required. There are some limitations, particularly regarding cost development, technology development, expected heat demands, and this requires, I think, that this task of a planning process is continuously adapted to this actually realized technological developments, cost developments, and heat demand levels in each area, but also on national and European level in total. Thank you.
Thank you very much, Lucas, for your presentation and your timing. That you are really on time. So we have questions. We have 5 to even 10 minutes for questions. So this question you can make by yourself, or either you can use the chat. I am checking the chat. There's no question in the chat. So I can ask you something. So in the meantime, if people get awake. So, for example, I mean, I haven't seen in your presentation any figure or any mention to which are the carbon gains. I mean, the emission gains in all these scenarios or in the transition. Have you measured this? Because I mean, your motivation is this, so you should need to show some numbers. Right?
Yes, so we actually calculated the 2 time steps, 2030 and 2050, and in 2050 we have full decarbonization. So yeah, there is simply no carbon emission left. I mean, if we exclude biogenic carbon emissions, from biomass. But so we have a pure climate neutral heat supply system in 2050. In 2030, indeed, that's not yet the case, and it's indeed a good question. What is the level of greenhouse gas emission reductions that we achieve until 2030? I would have to look it up in the results. I cannot tell it right now, but indeed, and I think it would also be relevant, as you say, maybe to calculate and display also the accumulated CO2 emissions over the whole period, which we actually have not done. because the focus was mainly on these, also according at least to our understanding of the requirements of the Energy Efficiency Directive in this respect, to focus really on this, yeah, on this achievement in 2050. But yeah, you're right. It would be an interesting additional evaluation of the results. Yeah.
Also, because you have this, I mean, you have data for the different regions. I guess that it would be very nice and very interesting to see the convergence pattern to this 2015 goal. So, I mean, it is not the same to go very fast than to go very slow. And it is not the same that all regions go hand by hand, so at the same speed, or that, I don't know, the richest regions go faster than the poorest regions. So it would be really nice to see this transition pattern. How no, because I mean, somehow you are like imposing that in 2050 there is zero decarbonization. So you are looking for which are the mix in order to get this target. So we know that we're going to get, I mean, according to your model, no, to your prediction. So I think that this, what is really relevant is to see what you are not imposing. That is this transition, this convergence pattern. So maybe this is another paper, but I think that and you can do it because I mean you have all data. So, and depending on the scenario you're taking, I think this is nice. And another question, so you can join this if anybody is that how these predictions can be affected by this crisis, the COVID crisis, because I mean, of course, the price that you're using, the interest rate that you're using. So, how a crisis like this can affect your predictions or your, this is another really relevant.
No, I completely agree. So the first question, the interest rate, I think is always very relevant and important, and at the same time very difficult to answer, because in particular also the long-term effect on interest rates is so unclear, I would say. But indeed, I think it's important to consider this point and or let's say to discuss also different levels of interest rates. I mean, that's what anyway was required to do according to Energy Efficiency Directive, and which I also think makes sense to distinguish different interest rate levels. But still, we also did not calculate a scenario with very low interest rate of almost let's say 0% or something like that, what we also can observe in reality now. Another impact on the of COVID, I think, will be on the or might be on the regarding the mix of heat demand in different building categories, let's say. So there are these expectations that the share of home office could increase in the future, which would mean that we have higher share also of space heating and hot water demand in residential buildings, and lower share and lower, in particular in long-term, lower floor area even for office buildings, or and that this would modify the mix of the building structure, and could also have an impact on the heat demand and the local concentration of heat demand. But this is nothing that we were able to analyze so far.
Yeah, but maybe for next paper, you know, to compare the COVID scenario, no, in comparison with your current scenario, no, and try to make the differences, and try to think how you can reduce the gap between the COVID scenario. So maybe you can adjust, or there is some possibilities to move another variables just to speed up, no, the transition under a COVID scenario. So I mean, it is an easy paper for sure that you can do, and this is a very highly impact right now. Okay, so I don't know, any questions? Any question for people in the audience? You can open your micro and do your question by yourself, or in the chat.
Excuse me, if I have time, I have one question. Thank you very much for your presentation. And my question is about cost for heat. According to the slide from 18 to 20, the cost, levelized cost in the 2050 appear to be higher compared with the cost in 2030. May I explain in the reason why the future cost is higher than 2030?
So the base, let's say it basically starts with these with the assumption that in 2050 we need to be fully decarbonized, and this means that we have either to replace fossil gas by green gas, which turns out to be expensive, at least to our both in the low and the high price scenario, and the renewable options are, the other renewable options are most cases cheaper than the green gas, I would say, but still somewhat more expensive than the current status quo. However, I would also say that comparing costs of in 2018 with let's say 2018 to 2030, which are strongly gas driven, and when we add the as we do in the socioeconomic scenario, the external costs of CO2 emissions, then we cannot say that the 2050 levelized cost of heat are higher. They are in a very similar range. Yeah, so about 40-50 euro per megawatt hour, and that's also the case even higher for the gas-driven portfolios when we add the external costs, which we again took from I mean the range of external costs estimation for greenhouse gas emissions is extremely high, from I don't know, 20 to 1,000 euro per ton or something like that, and yeah, we took this 300 euro per ton in our assumptions. Yeah, I hope this.
Thank you.
Yeah,
I understand.
Okay, so thank you very much, Lucas, Kengo, for your question. I think that we need to finish. So thank you very much, Lucas.
Thanks
for your presentation. Now let's move to the second presentation, that is by the Kengo Suzuki. That I know that he's here.
Yes.
Okay. And also this paper is co-authored by, sorry, but I'm not going to be able to say properly, Ryohei Ishiwata. And the title of the paper is How Carbon Tax Change the Perception and Behavior of Players in a Competitive Energy Market. So the floor is yours, Kengo. You have like Luca, 20 minutes and another 10 minutes of presentation, 20, 22, okay. We are flexible in that.
Thank you very much for introduction. And I'm very happy to speak to you today. Okay, so let's start. And as background, the energy transition from fossil fuels to renewables has not reached a sufficient level in terms of mitigating catastrophic climate change. To achieve the ambitious goals set out at the climate summit in December, and policymakers need to further introduce or improve energy and environmental policies. And among various policies, the carbon tax is one of the most fundamental policies facilitating the energy transition. However, the rate of carbon tax in Japan is less than $3 a ton CO2. It's too low. It's about it's very too low to encourage decarbonization by economic entities. So therefore, the Ministry of Environment in Japan is discussing a plan to gradually raise the carbon tax rate. The raise of carbon tax rate is expected to promote renewables by two mechanisms. The first is a direct effect by raising the procurement cost of fossil fuels. And the second is an indirect effect by the notice of future tax rates. The second effect means that policymakers expect that the economic entities will progress decarbonization in advance when they are noticed the raise of carbon tax rate in the future. And these mechanisms include dynamics of multi-agents who have both the rational thinking and the subjective assessment of future uncertainties. And however, the problem is that how to estimate the dynamics of such a multi-agent systems. There are roughly three types of methods to investigate the characteristics of such a multi-agent system: the game theory, agent-based simulation, and the game-based experiment. And among these methods, the game-based experiment is suitable to investigate the relationship between the subjective reality of economic entities and the dynamics of the target system as a whole. And the game-based experiments have been widely used in the field of social psychology and behavioral economics. In the context of energy and environmental policies, this method has used to verify whether the carbon market behaves as policymakers intended by comparing the results of games and different treatments. And so this study experimentally investigates direct and indirect effects of carbon tax on energy transition in competitive markets by applying game-based experiments. The experiments consisted of gameplay and questionnaire surveys. The gameplay is a record, and we obtain two types of data. The records of gameplays represent the objective aspects of the market, and the answers to questionnaire surveys represent the subjective aspects of the market. And by comparing the result of games and two conditions means without and with carbon tax, we infer the mechanism by which the carbon tax influences the selection of energy sources by market players. And from here, I'd like to explain the experimental methods. And for the purpose, we developed the multiplayer game named Energy Transition. In this game, the participants play the role of energy companies in a competitive market. The purpose of the participants is to maximize their own profits. And in every round, they make a profit by selling final energies produced from fossil fuels or renewables. In this simplified model, there are only two types of primary energies: fossil fuels and renewables. And in every round, the participants decide make three types of decisions: the energy mix, selling price, and amount of R&D investment in renewables. The game continues 30 rounds, while data up to the 25th round is used to avoid the end effect of the model. At the beginning, the cost for renewables is higher than that for fossil fuels, while the cost for renewables is decreased according to the R&D investment by players. On the other hand, the price of fossil fuels rise over time. So their value may be switched. The fossil fuels may be higher than renewables as game goes on. And however, there is a mechanism of market competition. And if the consumers move from companies with higher selling prices to these with lower selling prices in every round. So if a player make a too high selling price, he lose their consumers. This is a mechanism of the market competition. And there are mainly three core mechanics in this game. First, the profit of players in every round is calculated from the revenue of selling energy, production cost for renewables and fossil fuels, and around the investment in renewable technologies. And second, the change in demand is proportional to the deviation of selling prices from average value of all players. And third, the production cost for renewables is reduced when player invests in our research and development or actually supply as final energy by using renewables. The learning by researching and learning by doing. It's a typical two variable learning curves. And the formal model is explained in detail in the full paper. Excuse me. And the parameters of the model were set so that the game can represent the dilemma in competitive markets, the conflict between long-term investment and short-term competition. The number of players, number of rounds, and the competition-related parameters were empirically set by considering the results of preliminary experiments. And other parameters were set so that the optimal solution for players satisfies the three conditions below. First, all final energies produced from renewables at the final round of game, and the total profit through the game is positive. These two conditions ensures that the energy transition is profitable for all players in the optimal solution. And third is that the supply cost for renewables cannot be lower than fossil fuel in the first half of the game. And this third condition ensures that the energy transition is not easy and requires a continuous investment in renewables. And these conditions ensure the conflicts between long-term investment and short-term competition. And so initially, the experiments were planned to be held at the laboratory. However, the epidemic of the COVID-19 has made such a lab experiment difficult. So we newly constructed a completely remote experiment environment that does not require any physical contacts between the experimenters and the participants. We implemented the multiplayer game into a web application and developed an operation method utilizing a video conference system. The experiment environment consisted of a web application server and PCs owned by participants and experimenters. At the beginning of the experiment, participants access Zoom from any place they want, any location they want, and receive the explanation of experimental outline. After that, the participants play the game using web browser. The experimenters monitor the progress of the game via web browser and receive any question from participants via Zoom. All communications with participants, experimenters, and web servers was via the internet. From here, excuse me, this is a summary of experiments. The experiments were conducted under two conditions, and with and without carbon tax. In the with tax condition, carbon tax was introduced from the 16th round, later half of the game. And this taxation is equivalent to the rise in fossil fuel prices because tax revenues assumed not to be returned to the market. It's just a raise of the price as shown in the figure in the right-hand corner. And the timing of the introduction and the rate of carbon tax were informed to all the players in advance. And 56 students of our university were participated in 14 games, 7 games for each condition with and without tax. The reward is between the 2,000 to 4,000 JPY, approximately the 20 to 40 USD, according to the score of the game. And in these experiments, the subjective reality of participants were investigated by a questionnaire survey. There were two types of surveys, in-game survey and post-game survey. The purpose of in-game survey is to observe the changes in anxiety about uncertainty and the acceptability of carbon tax. These questions were asked in every 5 rounds, including just before the start of game. And the purpose of a post-game survey is to investigate the comprehensive understanding of gameplay by participants after the game. And from here, I'll show the result. This is the first result. This table shows the average value of results in gameplays under two conditions, without and with tax. As shown in the first line, the total renewable energy supply through the game is larger in the with tax conditions compared with without tax conditions. And the significant difference was found between these conditions at the 10% level. The final profit is also higher in the condition with tax, but no significant difference was found. And there was no noticeable difference in the other three summary values: selling price, R&D investment, and renewable supply cost. And these figures show the time series changes in the behavior of players. The first figure shows average renewable energy supply. The black is without tax condition, and red is with tax condition. And the transition from fossil fuels to renewables occurred after the 16th period in both conditions, but the rate of transition is higher in the with tax condition. The second figure shows selling price of final energy, these values, and the circle plots, and the supply cost for renewables, the diamond plots. The selling price decreases until 10th round, and then started to rise in both conditions. The rate of increase is larger in the with tax condition. The supply cost for renewables consistently decrease through the game, and there is few differences between conditions. The third figure is value of R&D investment in renewables in each round. The investment decreased as the game proceeded in both conditions, and there was no noticeable differences between the conditions. And this slide shows the results of the Mann-Whitney EU test between the two conditions for time series changes data: the total renewable supply, selling price, and R&D investment to renewables. And these values are total value, average value, and total value for every 5 periods. There were significant differences in the renewable energy supply in the 16th to the 25 rounds between two conditions. And there was also a significant difference in the selling price between 16th to 20th rounds between two conditions. But there was no significant difference in research and development during any rounds. And here I show the changes in the perception of players. And these figures show the time series changes in the answers to the in-game questions about the anxiety against uncertainty in games. The plot in the first figure shows these at the vertical values show the average value of all players participated in each conditions. The first figure is anxiety about the price competitions. This anxiety was between 4 and 5 through the gameplay under both conditions. The anxiety about investment in renewables and future fossil fuel prices are 4 to 5 at the beginning of the game, but it decreases later half of the game, as you can see. And for these perceptions, there was no significant differences between the two conditions. The trends were almost the same between two conditions. And this slide shows the answers to the post-game questions about the effective strategy, barriers to energy transitions, and impression of the game. First, players recognized that transition to renewables is the most effective strategy among these three, compared with keep using fossil fuel or hybrid use of renewable and fossil fuels in both conditions. And second, players regarded that the unclear relationship between the investment in renewables and the decrease in the cost for renewables is the largest barrier to the energy transitions. This value is both highest in the both of two conditions. And further, the competitiveness of market was also here. Competitiveness of market was also considered as an obstacle to transition under the without tax conditions. This value is decreased in the with tax conditions. The significant difference is observed only for the perception of the competitiveness in this market, only this one. And for other questions, there was no significant difference among two conditions. Discussions. The results of gameplay shows that carbon tax accelerated the energy transition in the later half of the gameplay, but neither promoted the transition of energy sources nor the investment in research and development in the first half of the game. These results suggest that the carbon tax directly changes the behavior of market players, while the notice of taxation in advance does not change their behavior. And the result of a questionnaire survey shows that anxiety of players during the game was not prevented by the notice of carbon tax before the game starts. This result suggests that the notice of future tax rate does not change the subjective recognition of uncertainty caused by the investment in renewables. Actually, the carbon tax reduces the absolute benefit of strategy of using fossil fuels, but does not guarantee a relative advantage over a strategy actively promoting the energy transition. If fossil fuel price raise only slowly, the fossil-dependent strategy may keep relatively high profit even after taxations. Conclusions. Among the expected effect of tax, the direct effect by raising the procurement cost of fossil fuels was observed, but the indirect effect by the notice of future tax rate was not observed. These results suggest that the carbon tax can contribute to energy transition only when it is introduced as soon as possible, and the level of tax is high enough to convince energy companies that investment in renewable is an optimal strategy. And another achievement of this study is that the empirical study of energy market can be held even under the epidemic of COVID-19 by utilizing the information technologies. This remote environment is useful even after the end of epidemic. It makes the collection of people and handling of experiments much easier and enable new types of research methods such as crowd experiments. That's all. Thank you very much for your kind attention, and I welcome any question and remarks. Thank you very much.
Okay, thank you very much for your presentation. And let me, Kengo, thank you. And I think that we have time for during 5 minutes for any questions the audience want to make, or maybe I can start asking something. Okay, so let me ask you something. I mean, just to clarify things. I mean, I guess that the reason, I mean, when you talk about a direct and indirect effect, I think that they are not really direct and indirect effect. I mean, they are like a short run effect and dynamic effect, right? I mean, it is the same effect. So it is the reaction that the consumers, or I mean the firms you're trying to, here is the player for the same type of decision, right? But one is like contemporaneous one, and the other one is if you are taking some decision in advance because of some future news or future change of taxes, right? So I guess that it's not direct and indirect effect. No, an indirect effect is when the consumer, the consumer or the player here reacts through the change in prices of other markets. For example, you are trying to measure also how we change the decision of buying cars or buying bicycles. So if a carbon tax increase, so it affects to the decision of buying gas, no, I mean, or gasoline. So the prices of cars go up, and then you change the decision for car buying. So I think that maybe this indirect effect, and maybe I guess that the reason why you don't observe this dynamic effect is probably because you are, I mean, it's very difficult because I mean you are trying to think that the student is like a company. So it's like a very difficult to believe that they think how to invest. I mean, the dynamic effect appears if you change your investment decision because you are looking in advance tax change. Maybe if you would ask, for example, a decision of buying an electric bicycle, no, and you say, okay, in the future we're going to increase the tax rate on cars, maybe they are going to buy, no, to change the decision on when to buy the electric bicycle, because I mean it is much easier for them to think on buying things than thinking on investment decision. I mean they are students, no, so maybe think on this investment decision is like a difficult thing. But I mean these are my comments. I guess there is somebody you can ask or you can comment. You don't need, but if you, I don't know, I guess that this dynamic effect, you need to think why it is not happening, because it should be.
And however, thank you very much for your comment. And I agree that the word, how can I say, direct and indirect may not be correct. It must be dynamic. How can I say, it's a short-term
response. No, contemporaneous impact and dynamic impact.
Temporal or okay, I understand what you want to say. And even they are students, I control the difference in the treatment, and I informed that carbon tax increases in the 15th or 16th round in advance. So even if they are students, they can estimate that the energy transition may be excuse me, not the energy transition. The cost for renewables, cost for fossil fuels may be higher by the taxation. So even they are students, I set the conditions as they can behave as actual energy companies. But if players are not students, but real energy company members, the results may be changed. It's another problem of such a kind of lab experiment. But I did my best to control the conditions and explain the impact of carbon tax to the students in advance.
It's very difficult to control. I mean, I think that the what I think is that your experiment is quite nice. Okay, it is really nice because you are obtaining things that they are really difficult to obtain. But maybe if the purpose would be like to analyze the decision of buying something that is no, I mean that the student know perfectly what is. To think and to put the student in a situation like the company is maybe too difficult, but this kind of exercises think that they are really nice for what I say, for example, buying electric vehicles or electric bicycles, and now they are very trying to put a lot of effort in increasing. So but they are nice. And another simple question, it is not affecting to your results that your experiment has been made during the COVID crisis.
Yes.
In the sense, it is not that everything is online and everything is using computers, but also because, I don't know, people are like in a different mood. Okay, maybe we are depressing, or maybe no, we feel that the war is ending, and I don't know, maybe how can you control that?
Okay, I
How
understand.
people feelings because of the crisis of the COVID?
Probably not exactly the same the direct communication and the internet communication. However, in the case of this game, players do not talk each other during the game, even before the COVID environment. Before the COVID epidemic starts, we performed this experiment in the laboratory. Even in that time, players did not talk so much, because the players must make their decisions within 3 minutes or 2 minutes in every round. So they have few time to discuss each other. So of course, the communication before and after game is different, especially the debriefing after the game. So the effect to the result of a game, not so large, I guess.
Okay. Any question? I saw like somebody raise his hand, but and now I can't see if the hand is up or not. I don't know if it is the technology or the person has down its hand. But is there any questions? Any other comment? Maybe we should move to the next presentation. Okay, so thank you very much, Kengo.
Thank you very much.
Nice paper, nice experiment. Okay, you have a lot of potential by developing this device.
Thank you.
And this kind of things. Okay, so we move to the next presentation. Sophie's.
Yes, good morning. Can you hear me well?
Okay, so we go to the next paper, the last paper of this session. It is the title is Lessons from the European Island Territory Decarbonization, the role of flexibility to ensure high renewable energy integration. And the authors are Sandrine, Selosse, Sophie Chlela, and Nadia Maizi. Okay, the presenter is Sophie Chlela. You can say your surname much better than me, for sure.
Yeah,
So
Sophie
go
Chlela.
ahead.
Yeah,
We have
thank you.
this 20 minutes, and we have also this 5-10 minutes of discussion. Okay, so the floor is yours.
Thank you, and thank you for your interest in this presentation, and special thanks for the organizers of this event. So I am a student in Energy System Optimization Master Program at the Centre the Mathématiques Appliquées in Valbonne, France. And we are here working on the GIFT project, which is an EU-funded project in the H2020 Research and Innovation Program. And I will be talking today about the role of flexibility for ensuring a high renewable energy integration in European islands. So to begin with the project background, with the outline, I will begin with the project background. Then I will talk about the island's energy system and the core subject of this presentation, which is the flexibility and the provided and relevant solutions of this project. I'll talk further to that about the long-term prospective modeling, and it is what we are doing at the CMA, and about the case studies of this project before ending with the conclusion and lessons learned. So about the project goals, the GIFT project stands for Geographical Island Flexibility. The main goal is to decarbonize the energy systems of islands, and this is done through allowing a high level of renewable energy integration in the energy system, while providing a visibility to the grid and to better manage its flexibility and plan its evolution. And this is done through developing synergy between the different sectors and, of course, reducing the hydrocarbon-based energies with the end of ensuring a sustainability of the solution and the replicability in other islands. So there are 17 partners in this project dispersed all over Europe and working on implementing the solutions in Norway, in Hinnøya Island cluster, in the north of Norway, and in Procida Island in Italy. And we are here in Armene, as I said, we are doing the long-term perspective modeling, but there are also other partners who are working more also on technical solution and project management to implement them in the demonstration sites. And these solutions will be studied for replicability on 2 other islands, one in Italy and the other in Greece. So why are we interested in energy system of islands? And first of all, because they present a lot of challenges, especially related to energy supply and economic development, because due to their remoteness and marginal situation, they do not acquire bulk price purchases for energy and energy services. And they present high vulnerability towards climate change impacts with the higher rise of sea levels and coastal erosions and the property damage that will occur on these small territories. But despite these challenges, we find a lot of support, especially in the EU, with the EU Clean Energy Package, where there is an initiative especially dedicated for EU islands. So this will help support the territories, in addition to the European islands and are usually endowed with renewable energy sources, and they can benefit from this, the lowering prices of renewable energy technologies, especially wind and PV, to invest in these power plants. And last but not least, the opportunity for islands is also to prove their commitments to the international climate conventions, such as the Paris Agreement. And this is, and for what I mentioned here, it is interesting to study and develop island-specific energy system models. So to pass now to flexibility, which is the core subject of this presentation, and it is found in several scientific and international community publications, and we find that it deals with the operation of the energy system, maintaining its instantaneous stability and long-term and supply of security of supply. It is also related to its reliability and cost effectiveness while managing the variability and uncertainty of supply, especially with the renewable energy integration. And finally, and the what is important also is to ensure this balance between the supply and demand at all relevant timescales. So I was mentioning that the international community is dedicated to this subject, and we find in the IRENA report on power system flexibility in 2018 definitions of the possible enablers for this power system flexibility through different solutions. And we can say about, for example, a technical solution which is storage that you may know about, is to store the electricity while there is a high production periods and release it during low production periods, which most often coincide with the high peak of demand. And from another side, and mostly it is related to a strategy, and from the, as the name suggests, the demand side management. It's more about providing strategies to consume electricity during low tariff times and reduce consumption during higher and high peak of demands. And this is also enforced by the availability of IoT technologies to be able to connect the consumer side and the producer side. And finally, the sector coupling to that where the electricity can be stored in several sectors, and this is related directly to developing synergies between the sectors that constitute this energy system. So now passing on to the project solutions, there are three levels related to flexibility, but we are in the grid IT platform with prospective modeling and long-term assessment. But I thought that we can also take a look about the other solutions, especially the ones that related to the consumer side, because they are directly, they are all connected to each others. And here the consumer is called prosumer because it is a consumer that can postpone its energy demanding tasks and or select alternative sources of energy. And this is all done by optimizing the production and the consumption through an energy management system and sending signals to the virtual power plant called the VPS control center. And why are we what is the doing? Why are we doing long-term perspective modeling? For instance, we need to define an energy plan. Operators or on the energy system need to define an energy plan on the long term, and it should be a reliable system. So decisions should be made related to the investments and technology, their types, their capacities, and also where these capacities should be installed. And this is pretty relevant to the case of islands because they are limited in their surface. So this is all can be studied through long-term perspective modeling while considering several and different evolution scenarios. And the tools that we use in the CMA is the Times Integrated Markal system, which is developed by the ETSAP and based on techno-economic optimization while taking into account the environmental, social, and political constraints. And at the end, we will be able to advise the policymakers and authorities, such as the operators, to make knowledge-based decisions and implementing adequate energy planning. So now talk more about the Times modeling, the tool. It is an economic model generator, and it is based on a partial equilibrium linear programming. It is a bottom-up technology-rich driven by demand optimization model, and it takes as inputs and it can take as inputs. It describes actually the energy and materials flows that coming from primary sources or imports, and while taking account of their costs. It aims to minimize the net present value through this equation and summing it throughout the years of the horizon of the periods and the regions of that are studied. And the annual cost here, there can be anything from CAPEX to OPEX, and also taxes and subsidies that are related to commodities consumption, and they are multiplied by the total discounted system cost. And for this demand that are service demands, so we can input this exogenously and with through different either projection on the demand provided by reliable sources or inputs of the GDP and population growth and to predict the future demands. So now to pass on the case studies, there are the island in Italy called Procida. It is the smallest island in the Gulf of Naples, and you can see it's quite dense in terms of inhabitants. It presents challenges related to the grid congestion because it's connected to a nearby island also through a submarine cable, and has the problem of high seasonality of demand due to tourism activities. And the second island is the Hinnøya island cluster located in Norway in the north, and it is a large island, but it presents challenges with the limitation and of possibilities of new grid connections. And as you may know, in Ireland, in Norway, fish farming is quite famous, and this sector in near this island is still using diesel generator and emitting greenhouse gas emissions. So here we can see the geographical location of Hinnøya Island cluster, and why are calling it a cluster, because it's constituted by a small island cluster, and the whole part of it is the Hinnøya Island cluster. And the small circle here is the Harstad community, which is the center of economic activities, and where mostly we can find the solutions deployed, like the factory energy management system, which will help the consumers reduce and defer their consumption period. And also, and what I will be talking about is the electric vehicle and charging station deployment on this island as a flexibility solution. But first, let's see the energy profile of this island. As you can see, 63% is based on imported electricity from the national grid. And this is somehow a good news for the island, because Norway's electricity is at 96% from hydro. So we are talking here at decarbonized electricity, which is used in the economic activity sectors. But except the fish farming at some extent. And the remaining, we see here that fossil fuel is used, quite used, because transportation sector relies on it, and it is a necessary sector to move around the Norway due to its geology. So why are we interested in the EV or electric vehicle deployment, especially on the long term? As we find in Norway, at the national level, we find targets that aim to reduce the emission cuts from this sector, like reaching 40% emission cuts, and also a lot of incentives related to the deployment of electric vehicles, with removing the tax on registration and the road usage tax, for instance, and most recently, which already exists, a taxation on the fossil fuel consumption, but now Norway is thinking of gradually increasing it. And on the local level, we see that there is indeed an increasing trend of electric vehicle deployment, especially in the Harstad community. So, and in this project, we are talking not only about the EV deployment, but the EV charging and conditioning this charging of vehicles through active control. It is about unidirectional control, so vehicle to grid to vehicle, and the flexibility is offered by individual charging sessions whose load is shifted from peak hours to off-peak hours, and this is for releasing the stress on the distribution grid, but also charging control can reduce the power, not only the timing of charging. And To do that, we needed to model the electric vehicles and the EV chargers, and we used fuel economy data and capital costs, as well as OPEX costs and the lifetime of these of the vehicles and the chargers. But also they have to use future transport demand services, as well as future electricity forecast, because this method is based on the variation of the tariffs, electricity tariffs. And in addition, and since it is a policy or implemented in Norway, the taxation on transport greenhouse gas emission was implemented. And as you can see here in the graph, in the blue line, the shift of charging is with the low prices of electricity. And when we have peaks, the immediate shutdown of charging. And also to point out that in this case, since the people in Hinoya, they work from 7:30, so they tend to plug their vehicles at 7:30. This will not be, they can offer their flexibility by reducing and not plugging, or plugging, but letting the control system reduce their charging at these hours, and also before leaving work at 3 p.m. And we can see the impact of this EV charging strategy, that it smooths the so-called duck curve by a phenomena called load filling at the low peak demand times, and no additional demand is made during peak times. So now to pass to the Proshida Island, and you can find a lot of details about it also in the abstract. But the main source of electricity comes from imports, and 99% relies on the submarine cable, with small percentage really of solar PV. And exploiting this, the photovoltaics on this island will help reduce its dependency on imports, and also enhance the decarbonization of sectors, which you can see here all use electricity, and the biggest consumer being the residential sector. So in the model, there was a constraint by the surface area of the PV installation. As I mentioned before, it's a small island, and the PV panels will be invested and installed on buildings as residential, tertiary buildings, and public buildings. But if we consider a high scenario, so going to the maximum of installation, the model prefers investing in public and tertiary buildings. And if you want to more invest in flexibility with the storage of lithium-ion batteries, the model chooses the public buildings. However, this is a good news because we see a reduction in electricity imports more than 50% starting 2025, which directly reduces the total imports at peak hours, and we see here at 2025 with minus 0.61%. So to conclude and to see here the final energy mixes of the islands, we see that there is, with the flexibility solutions applied by the project, we see a higher integration of renewable energy sources in both cases. But for Proshida, it's more about the self-consumption, and as for Norway, it's related to cross-sectoral integration of renewable energy and flexibility, and through the electrification of the transport sector. And the main key takeaways are the importance of assessing the context of the territory, not only the energy system of the islands, because this will help understanding what are the flexibility needs and identify the suitable solutions. Also, we have noticed that the flexibility is linked to investment costs, such as the case in Prashida, since the system was more investing in different sectors, especially with the integration of storage technologies. Also, we found that long-term planning supports indeed the decision-making in new investments and flexibility solutions, but it is limited from a grid operation point of view. So in this case, and which is good in this project, that a lot of collaboration is happening between the different partners, and with the other solutions implemented in this project, we see that we can have a better visibility on the grid. Also, we see that there is a necessity of involvement of the consumer, and that becomes prosumer, and they participate and become more aware of their energy consumption and participate at the end in the energy transition. Finally, there should be a permissible regulatory framework in order to implement all of this information and technology and communication systems, as well as regulating the work of the solutions and the grid. And this will also help in ensuring the sustainability of the solution on the long term. So this is what I wanted to say. I can now show you the references. And thank you very much for your attention.
Thank you very much, Sophie. We have time for 10 minutes questions, discussions. So I wait until somebody raise his or her hand. Okay, you should include in this project Tenerife and Canary Island as a a case study in the next round of the call. Okay, in the meantime, maybe I am ask you one question. I mean, maybe I didn't understand, or I didn't see in your presentation, or I get lost at some point. I mean, are these islands, the two examples, the two case studies that you are doing, really isolated in the sense that they are they connected by cable or not?
Yes, they are, both of them are connected. And this is how they import their electricity. And for instance, Italy, in the case of Italy, it's the submarine cable. And for the case of Norway, here the small islands are connected to through a submarine cables to the main island. And the main territory is connected to the main grid of Norway through North Pole, region 4.
Okay, so they are not isolated systems like the Canary Islands, for example.
Yes,
the Canary Islands are Azores and Madeira. They are isolated because they are not. We're trying right now to make a connection between several islands, but we are not connected. We are too far, and the ocean is too deep that we cannot connect. So, I mean, that would be real an additional challenge, because if you cannot connect, I mean, you can import energy, but the energy you can import is gas, basically, and oil and diesel, no more than that. So there is more challenge in this set of islands. So maybe I don't know if with your technology or in the scope of the project, it would be really nice to include this kind of exercise.
Yes, actually, this project, the two islands are connected through electricity imports. But for instance, there are other islands that we studied at the CMA. For example, the island of the Reunion, and it is not connected. If my supervisor is here, can correct me if I'm wrong. And so it is quite challenging. It's a different aspect to study, and that's why we are more in such islands. It's more interesting to also invest on renewable energy production inside of the island. So this will help increase the independence of the import, because also doing submarine cables is quite expensive. And here I wanted to show you, since we have time, we studied also the investment in renewable energy technologies on the island of Hinoya. And we studied with the hydro and the diesel to hydro and wind, the investments, and we see that the import of electricity is reduced, since this island has the potential in these two hydro and wind, but they are not included directly in the project. So this is what an additional to try on that. And yeah, so actually this increases the independence.
Yeah, I mean, here the main challenge, I mean, the main difference between the unisolated islands and not is that you can substitute the storage by import electricity from an island. But if you are isolated, the only way to increase renewables is that you generate a complementary system to storage the electricity. So I mean, the story changed dramatically. So it's totally different, the story, and totally different. So it would be really nice to compare two islands with similar characteristics, because I guess that these two case studies are more related with a rich island, poorer island, right? I mean,
from not the developing
state, Mediterranean or North. So they are different enough
yeah, and and both of them have problems in the electricity grid. So the congestion problems, or the limitation, and so flexibility solutions are quite applicable in this case, especially with the storage, as you mentioned, and also the controlling and shifting the demand.
Okay, any questions? I just only to finish, I have to say, I don't know, I am a little bit worried when I heard in these models that they are of partial equilibrium models. Because I mean, it is like no, we are just looking at part of the story and not the whole picture, because by assuming a partial equilibrium model, you are basically assuming that any change that you're introducing, a lot of changes in this no, in the electric system are not affecting prices in other markets.
Yes, exactly.
Like a strong assumption, right?
Yeah, exactly. It doesn't take into account the rest of the economy. It is more related to the energy system. So yes, this is what is the partial equilibrium, and it's more on this side.
You can a little bit overcome this potential criticism maybe by assuming a lot of scenarios. In the sense, I mean, in this case, when you assume, okay, let's assume a particular path of GDP or particular path of population or prices or real interest rate or whatever. So maybe like performing a kind of Monte Carlo simulation method that no, you assume a lot of potential scenarios, and at the end, in order instead of showing just values, show like a distribution of all potential situations.
Yes, exactly. That we do assumptions and scenarios, and we use the Monte Carlo.
Okay.
Yeah.
Okay, this is a way to overcome it. I am a little bit worried about the partial equilibrium models, but I mean, this is my I'm a macro guy, so from macro. Okay, so any further question? I hope to see this application for an isolated system, Canary Island better, Tenerife even better. So I don't know, anything else, or we can finish the session so we can have a coffee before starting the next session.
Maybe we would exchange our emails for the participants, and so that
Okay.
when my email is here, I will copy it
That's a good idea. Hey, we can copy in the
on the chat.
chat.
Yes.
Copy all emails in the chat. The person that want to share the.
One last thing also, for the speakers, could you please upload your presentation on your dashboard? So on the website of the conference, please. And thank you very much for these very nice presentations.
Okay. Let's wait for the emails and we can close. I understand that you close for us, right?
Exactly.
Okay, perfect. So wait just only 1 minute. Thank you for the coordination.
Is there any other?
Is that any possible to upload also the full paper?
I really don't know, but I think so. I think that they can upload what they want.
Okay, I'm gonna check in the session management. Okay, I guess that we have here the image, right? We have Kengo, we have mine, and another one. So okay.
Okay, so then
Thank you very much.
bye.
Bye bye.
Bye.
Have a great day.